Hi everyone, I am Manasi Wijerathna from GHD, Sydney, Australia. The, the topic I'm presenting today is T-shaped DCM columns in preventing excessive deformations in embankments. The overview of my talk today. First, I will talk a little bit about deep cement mixing technology and column configurations, then the case study and the proposed design options, followed by numerical modeling, the results, and finally the conclusions. First of all, for those who are not much familiar with deep cement mixing technology, this is mainly a soft soil improvement technology. In this method, a bonding agent such as cement is mixed with natural soft soil using auger equipments to form a columnar formation. These columns are expected to transfer loads from embankment to the underlying strong soil layers. They are also used to stabilize, to provide the overall stability and to reduce settlements. However, they are not meant to take 100% of the loads as piles do. A common problem found in when using deep cement mixing technology is high differential settlements between the native soil and the improved DCM column. To overcome this one, usually a load transfer platform is used along with geosynthetic reinforcement. However, in recent years, new column configurations have been proposed as an option to this load transfer platform. One of these new column configuration is T-shaped DCM columns, as shown in the right-hand side figure. In these columns, the first couple of meters of the column has a higher diameter than the rest of the column. They are expected to provide more bearing capacity and less differential settlements. The case study we investigated in current study is a DCM column improved embankment in Ballina bypass section of the Pacific Highway Upgrade Project in New South Wales, Australia. In this embankment, beneath the crest of the embankment is improved with deep cement mixed columns, uniform individual deep cement mixed columns, and beneath the slope of the embankment is improved with DCM wall panels, as shown in the plan view here. The expectation of using DCM wall panels beneath the slopes is to reduce the lateral deformations. However, in the case study, once the embankment is built up, the embankment it experienced higher settlements than expected. It was also found that the deep cement mixed columns has been yielded near the center of the embankment. So the objective of our current study is to propose different other column configurations, other design options that would perform better than the actual design case. The different options that we proposed in this study are listed here in this slide. In option 1, we considered uniform individual DCM columns beneath both the crest and slope of the embankment. In option 2, we combined geosynthetic reinforcement along with this uniform and individual DCM columns. Option 3 and 4 are T-shaped DCM columns beneath both crest and slope, where option 4 has geosynthetic reinforcement as well. For this study, for this purpose, we used finite element modeling developed in ABAQUS software. In the figure, you can see the finite element mesh we used for the case history condition. Another interesting fact we incorporated to this study is modeling of strain softening behavior, post-yield strain softening behavior of deep cement mixed soils. For this, we used an extended version of the Moore-Coulomb model where we reduced the cohesion, peak cohesion and peak friction angle with the increased plastic deviatoric strain. Let's have a look into the results. First, the settlements. The black line shows the settlement profile observed in the case history. As you can see, the center of the embankment underwent higher settlements. However, the settlements beneath the slope of the embankment was much less because of the wall panels used. When we use only the individual DCM columns everywhere, we can see that the settlement, the spread of the settlement has been more wider. And also, the settlement is pronounced even beneath the slope of the embankment as well, although there is less load. When we incorporate the geosynthetic reinforcement into these individual DCM columns, we can see that the differential settlements has reduced compared to the option 1, and also the overall settlement as well. However, the settlement reduction is only about 7% compared to option 1. A great improvement was observed when we improved the embankment using T-shaped DCM columns. As you can see here in the purple line and blue line, the settlements are much less, even beneath the slope of the embankment. However, the differential settlement are anyway smaller, irrespective of whether the geosynthetic reinforcement was used or not. This reduction in settlement was more than 50% compared to the original case. Looking into the lateral displacements, the case study shows lateral displacements up to about 70 millimeters. As you can see, within the soft soil layer, the columns shows sort of a bending type failure mechanism. When we shifted to individual DCM columns, in option 1, as you can see, the lateral deformations were much larger and the failure type was column tilting type failure. This tilting type failure was reversed and it was holded very well once we incorporated the geosynthetic reinforcement in option 2. In fact, the option 2 showed 30% reduction of lateral deformations compared to case history. When we have a look into the geosynthetic tensile stresses, it was about 183 kilopascal stress inside the geosynthetic, which shows that it has been functioning very effectively. Conversely, when we come to T-shaped DCM column configuration, the lateral deformations did improve up to about 45 to 52%. However, the geosynthetic layer was not that effective. There was only 81 kilopascal tensile stress in the geosynthetic reinforcement. So T-shaped DCM columns itself could perform much better compared to case history as well as option 1 and 2. Coming to the conclusions, it shows that the T-shaped DCM columns improved the lateral stiffness and bearing capacity of the subsoil layer better than the combination of individual DCM columns and the DCM column walls used in the case history. However, it should be noted here that the area replacement ratio of the columns that we used for the T-shaped DCM columns and for the case history are not exactly the same. Second point, for the considered case history, the T-shaped DCM columns indicated yielding below the length of the column head at a depth of 3.75 meters. However, these are not as high so that it goes into the post-sealed softening zone. Geosynthetic reinforcement contributed significantly in reducing lateral deformations and differential settlements when used in combination with uniform DCM columns. Geosynthetic layer is less effective when used with T-shaped DCM columns. Before I end my presentation, I would like to acknowledge Associate Professor Samantika Liyanapathirana from Western Sydney University, who co-authored this paper with me, as well as supervised my PhD work during these studies. Thank you all for listening.